Hello, and welcome to the video lecture for Chapter 22, titled Stars from Adolescence to Old Age. Okay, so there's three big takeaways that I think we can summarize this chapter with. Number one, why do stars get bloated when they die? Okay, sounds morbid, but it just refers to the fact that stars get really big as they finish their life cycle. Okay, so that's one big idea. I want to touch on that a bit. The other one, how can we date the age of star clusters based on how many stars have left the main sequence? Okay, and then kind of topic three is what is this idea of stars getting bigger as they die? How do we understand it with a few more details, including how it applies to particularly big stars? Okay, so kind of introductory idea to motivate everything, relate it to something else, star clusters, and then provide further details. Okay, so that's what this chapter is all about. It's pretty concise. I think we can tie all those ideas in together nicely. So let's start off by looking at a nebula that represents the explosion of a star. All right, so here we have, it's called the Ant Nebula. It's a beautiful region of expelled gas, covers 3,000 light years, or it's a distance from about 3,000 light years from the sun. All right, and it's a bunch of ejected mass coming out in lobes. What's going on? What's happening there? Well, it's a star that's shedding material. It's losing mass. Okay, so one big idea that we want to talk about is stars leaving the main sequence. Okay, so do you remember what the main sequence is? Right, it's that part of the HR diagram. It's the big slash, right? Not linear, but that kind of diagonal curved slash right down the middle of the HR diagram, which plots luminosity versus temperature. Okay, that's the main sequence. That's where stars spend most of their lives. That's where stars convert hydrogen to helium. Okay, that's what it's all about. That's what stars do for the most part. But eventually they stop. Eventually they use up most of their helium. Okay, well, they use up most of their hydrogen and they have leftover helium. Okay, so here's the idea. This is a main sequence star. It's got a stellar envelope. Right, this is all the layers of the star outside of the core. And then there's the actual core where all the fusion happens. Okay, that's where the actual physical property of fusion is happening, changing hydrogen to helium. But eventually, most of the hydrogen has been changed to helium, and you have a bunch of leftover helium. It's like a byproduct of the fusion. And so you end up with a helium core. Okay? So then what happens is that helium core starts to collapse under the influence of gravity, because the only thing that was keeping it from collapsing in the first place was the outward pressure caused by fusion. But with fusion running out and petering out, not being as energetic as it was before because there's not as much fuel to go, that means that gravity takes over again. And as the helium core collapses, it heats up the immediate vicinity of the star, and thus a hydrogen burning shell is formed, because there was always hydrogen outside of the core, but it wasn't hot enough outside of the core for that hydrogen to fuse. But when the core begins to collapse and starts generating heat due to that gravitational collapse, finally that hydrogen does start to fuse, and we have a hydrogen burning shell. And by burning, we mean fusion. All right? So, as that happens, what happens to the star? It gets really, really big, okay? And to understand that idea, it's all about energy. Because what's happening is that all that extra hydrogen that wasn't burned before now is hot enough to burn. And so that's generating heat. That heat is pushing out to the outer layers of the star. Meanwhile, the helium core is collapsing, creating a huge amount of gravitational heat. Okay, gravitational potential energy is being converted to heat. And then that heat is flowing to the surface. So the overall effect is you have this all of a sudden overheated star. And what do overheated things do? They get bigger, right? Think about a balloon heating up in the sun. It gets bigger and bigger until it pops. Okay, so these stars get massive and they become red giants. All right, and they're actually generating more energy than they did when they were on the main sequence. So the luminosity, is driving that expansion. But what eventually ends up happening is as they expand, they cool off, because that's really kind of it's an outlet. That ability to expand and cool is all the star can do besides explode. And it's possible, those layers aren't adhered. It's quite possible as a gas, as a plasma, so it does expand. And so these giant red stars, red giants, they get bigger and they get cooler. And so we're going to see that on the HR diagram. And just for, kind of idea here, right? Here's the sun, a main sequence star. Here we have a couple of red giants, right? This is just showing you how much massive they are. And that really kind of puts into perspective, right? This process, it just gives you an idea how dense stars are when they're on the main sequence, and how when they start to, when their core starts to collapse and all that energy starts to get pushed to the surface, they get so much bigger and so much less dense, okay? So their size gets dramatically larger. This shows a good example of a red giant, Betelgeuse, which is a well-known bright star that you can see with the naked eye in Orion's belt, okay? Well, so the thing about Betelgeuse is here's the size of the star, okay? Here's its actual size. And here's comparison to Earth's orbit, right? So, this goes to show that a star that big would dwarf Earth's orbit, right? That's 1 astronomical unit. That's 1 AU. Earth's orbit, that's quite a bit bigger, right? It's 150 times bigger than the diameter of our sun, right? So our orbit's fairly large, but Betelgeuse is ginormous, right? It's huge. And furthermore, look at it. It's almost the size of Jupiter's orbit. Okay. Now, will our star get that big when it becomes a red giant? Not quite. It'll become big enough to engulf Earth's orbit. So, say goodbye to Earth, but it won't get all the way out to Jupiter's orbit. Okay, which is quite a bit further. So, but our star will become massive in its end of its lifespan, right? As it's going towards its final demise, which we'll talk about in the next chapter. By the way, we're not going to talk about the final end. We're just going to lead. This is just adolescence to old age. Okay. Adolescence you can think of as main sequence, right? Old age is going to be a big focus of this lecture here. But let's continue on. All right, so here's kind of the diagram that sums up what a lot of them are saying, right? This idea that stars, they're going to get bloated, they're going to get bigger as, again, the idea you got to remember, as the hydrogen runs out in the core and the leftover helium collapses and a outer shell of helium fusion begins. Okay, those are the processes that then lead to the star enlarging and becoming cooler. So what do we see, right? So we see stars. Let's look at one like the sun, okay? So here we have one solar mass, our sun. What's going to happen, right? So it's going to go up and it's going to follow this track, okay? And so it's going to get up to a point where it's more luminous and cooler, okay? So it's gone, look, so it's moved in this direction and it's moved in this direction. So it's increased in luminosity. So wattage, it's getting off more power, and it's become cooler. Now the biggest stars, they basically just become cooler and their luminosity doesn't change much. So we can see the very biggest stars, they kind of stay flat. Okay, the luminosity just creep up a little bit. There is an increase. There's always some increase in luminosity, but it's much more dramatic for stars around our size. Okay, maybe 1.5 solar masses as well. There's a big increase in luminosity. Because again, just the particular way that the helium core collapses, and we'll talk about briefly at the end of the lecture, because that's kind of the end of the line for stars of our size, because there's just not enough heat to then continue to fuse heavier elements. More on that in just a minute. All right, so that's why there's a big increase in luminosity and a not dramatic decrease in temperature. Obviously, look, the more dramatic decreases in temperature occur at these bigger stars. Right, notice? Okay, so you see that trend? Okay, smaller stars tend to go more up in luminosity and a little bit down in temperature. The biggest stars only creep up a tad in luminosity, but fall off precipitously in temperature. And they become even bigger, right? These are like the supergiants. Our star is never going to become a supergiant, our sun. It's just going to become a red giant. But they do have a lot in common, all these big stars. They're all leaving the sequence and they're all moving in the same general direction, right? They're all moving to the right and up from the main sequence, okay? So do take note of that, because it's important to see the trend and not get lost in the details, okay? All right, so here we're looking at a variety of stars. Really looking at their wide range of different colors, all the different life cycles that we're seeing. Okay, so let's move on. Let's move on to this idea of clusters then, because there's certain clusters of stars, and those clusters, as we know, can represent stars that were all born in the same place. Because there's one thing to see a cluster of stars from our perspective, and those stars could just be thousands of light years apart, but they just appear close together because of where we're standing on Earth. But sometimes when we see a bunch of stars cluster together in the sky, they're actually close together in true space, because they were all born from the same nebula, right? That is the idea we've been talking about, how stars are formed from molecular clouds, okay, relatively cold molecular clouds, okay, collapsing under gravity, just like the core of stars collapse under gravity, common theme there, right? Okay, so how do we talk about clusters of stars, star clusters? Well, we can think about them and we can age those star clusters based on the proportion of stars that they have in them. Let's look at an example, all right? So here we have a young star cluster, okay? And we know it's a young star cluster based on just looking at all the stars and putting them in the HR diagram. Because look what's happened. We have stars up here that have already got onto the main sequence, okay? So these are middle-aged stars, okay? Because really, I kind of said, oh, well, think of the, of the main sequence as adolescence, but not quite. That's more of middle age, okay? It's where you spend most of your life, okay? These are the adolescent stars because these aren't the red giants, that you might think, oh, wait, aren't they? They are, after all, to the, to the left or, to the right and above the main sequence. But it's more about looking at the way they're coming on. Because if you remember, protostars came from the right, okay? They came from lower temperature and less luminosity, and they came in this direction. So these are all protostars, okay? They're not on the main sequence because they're not actually stars yet, okay? That's why it's young. This is adolescence. Okay, the protostars are adolescents. They will be on the main sequence, but it takes them longer. These very hot, bright middle-aged stars, they got on the main sequence faster. Because if you recall, and we'll go back and review this, the time it takes to go from protostar to true main sequence star once hydrogen to helium fusion begins, that time is dependent on the size of the star. Bigger stars go faster. They get on the main sequence faster, and they also die faster. So these stars are able to get on the main sequence fast and then eventually leave it in much less time. We're talking, stars over here, right? They might take, hundreds of millions of years to get on the main sequence. These ones could take billions of years to get on the main sequence, whereas stars up here only take tens of thousands of years to get on the main sequence from protostar. So really dramatic difference in terms of the actual length of time, okay? So, but then we look at this, we can tell it's a young cluster because the only stars that are on the main sequence are the high luminosity ones. It's as simple as that, okay? All right, here's an actual picture of a young cluster. Now, what about a cluster that, looks different, okay? So this is, instead of theoretical, perfect data, right? This was like really nice, clean data. This is real data. But notice it has the right form. It's got brighter stars that are on the main sequence, and then it's got a bunch of other stars that aren't on the main sequence yet. It's got some that maybe just weren't formed at the same time, right? So the data doesn't fit perfectly, but it does show the real trend, right? So this is real data backing up the theory, okay? Okay, but what about a cluster that is older? What does an old cluster look like on the HR diagram? Okay, so again, this isn't real data. This is like more hypothetical, but this is an example of a cluster that's quite a bit older. Because look what's happened. There are no big stars, because they're all already completely gone. They've gone supernova. They're not even left anymore, okay? And the stars that are, in the middle range of luminosity, they've already started leaving the main sequence, and some of them have become full-on red giants. So the only stars that are left on the main sequence are the slow-moving, low luminosity, low mass stars, okay? So these ones took a long time to go from protostar to main sequence, and they're going to stay on the main sequence for a long time. And the fact that they're the only ones that are left means that these are old stars that are going to stay on the main sequence for a long time. All right? Okay? So that's the idea. You look here, you look at this shape, you compare it to the other shape. This shape tells you that this is an old cluster. Okay? So just the distribution of stars and how many of them are in main sequence can date clusters. And think about how helpful that is for astronomers, that they can piece together this information and say, oh, well, that cluster of stars must be, it's around maybe 600 million years, or maybe 1.5 billion, They can get that information just based on how the stars, as a population, fall in the main sequence, okay? All right? So here's an example of a very old cluster, right? Look what's happened, right? It's like just the oldest ones are in the main sequence. These ones have all gone red giant, okay? And these ones are completely gone. The absence of those stars that burn bright but die young, right? That tells you that they're completely out of the picture. They were there once. They were part of that cluster, but they're long since gone. Their entire life was done in a few 100 million years, or even tens of millions of years, and there's just nothing left. Okay, these ones here, by the way, are going to be around for like 30 billion years, right? These stars are so long lived that if they don't get wiped out by another star or a black hole or something, they're going to live much longer than the current age of the universe. That's how stable some of these small mass, low luminosity stars are. Okay, and of course our sun is kind of in the middle, right? Oh, here we are, a little bit more accurate. Ours is right there. Okay, all right. So here we have an example HR diagram for a cluster. Note the scale of luminosity differs, right? But look, it's got this shape, right? We have these stars kind of coming off the main sequence. We have stars on the main sequence. Okay, this is just zoomed in on one part, right? This isn't showing all the stars that don't exist up here because it just cut them off, right? Because notice a different scale. Normally the scale goes up to 100,000 times brighter than the luminosity of the sun. This one only goes up to 100, so it's zoomed in. In other words, it's just zoomed in on this part. Okay, see the behavior. Okay, all right. So this is just really elaborating on the idea, right? Here we have newborn, at least at some hypothetical point, if you had all the stars start on the main sequence. But of course, we saw that really young clusters, they don't all start on the main sequence because these ones take longer to get on the main sequence, right? But if you had before they actually get there. But if you had a point where you had a group of stars that would all happen to be on the main sequence simultaneously, what then would happen is then these ones would start turning off first after about 100 million years, so not very long in terms of stellar time scale. Okay, remember the age of the universe is 13 billion years, okay? And then after about 10 billion years, so much, much further, right? These ones are all gone already, completely been eliminated, blown up, right? Gone supernova. And then these ones are in the red giant phase, right? A kind of much longer lived red giant phase. And these ones are still in the main sequence. And they're going to be around for a long time, okay? All right. Okay, so a little bit more detail now. Now we're on to the third chapter of this lecture, okay? The third part of this lecture, because after all, it's all one chapter, right? Not to misuse the term. But this is a little bit more detail about this idea of becoming a red giant, because that's what we started the lecture with. Let's end with it. So here's the idea, right? So stars like our sun take a particular path, and there's a little bit more detail than we showed before, where we just said, oh, well, they're on the main sequence, and then they go up, and they become red giants, which means they become significantly more luminous, and also a bit cooler, okay, and quite a bit bigger, all right? But what's actually interesting is that there's a little bit more to it. They go up, okay, so they're expanding. This is the part where the helium core is collapsing. Well, let's look at one letter at a time, right? So A, the star evolves from the main sequence to be a red giant, okay, decreasing in surface temperature and increasing in luminosity, as we discussed. But then we get to part B. We haven't discussed this yet. Part B is something called the helium flash, okay? This occurs, this leads to a readjustment of the star's internal structure, okay? So that's the part where we have the core actually starts to fuse helium. The core is collapsed so much that it reaches this critical stage where it does start to fuse helium, okay? And so then we get down to part C, a brief period of stability during which the helium is fused to carbon and oxygen, right? That's a whole new process in the core. All right. In the process, the star becomes hotter and less luminous than it was as a red giant. So it actually will shrink back down. Okay, shrinks back down to stage C. Okay, and at stage C, doesn't last nearly as long as the main sequence, but now it is a helium star, and that's a term that sometimes people use, helium stars. And essentially, that means that instead of burning hydrogen, burning in quotes, and turning into helium, it's now turning helium into carbon and oxygen. Okay, so it's still fusion, but since it's a different type of fusion, it's not quantified as main sequence. And also we see anything that burns helium won't fall on that same trend line, on that main sequence line. It's going to have a different value of luminosity versus temperature. Okay, they're plotted in a different point. But it is quite fascinating to think that stars can survive off of actually fusing helium. Okay, totally different process, different physics. Right, really, and this is where carbon and oxygen come from. This is why carbon and oxygen are relatively common elements. It's so neat to think about, that where the building blocks of life come from the inside of stars. Okay, because by the way, carbon and oxygen were never made at this point, right? Up to this point, when stars are in the main sequence, they don't produce carbon and oxygen. It's only once their core is already collapsed and they've already gone through a red giant phase that they actually start doing that. All right. Okay, but then that doesn't last forever, right? It's going to last for a fraction of the time. It depends on the star, but we're talking, as a lifespan of a star like our sun is 4.5 billion years. The phase through which it becomes a helium star is only going to maybe be 100 million. Okay, so then we get to part D. All right, stage D right here. So now we're going back up, right? We're expanding again. Why is that? Well, after the central helium is exhausted, obviously we ran out of fuel again. Every time we run out of fuel, what starts happening? The core starts collapsing. As the core starts collapsing, that heat has to go somewhere, thus expansion of the star, cooling of the surface temperature. Okay, so the star becomes a giant again and moves to higher luminosity. Okay, so it's going up, all the way up. Okay, and lower temperature. By this time, however, the star has exhausted its inner resources. It's never going to get hot enough inside to fuse. Burn is the term, right? But this is the colloquial term. It's never going to get hot enough to fuse anything heavier. It's never going to it's never going to become the next level of star. But we will briefly talk about stars that can. Okay, because by the way, this is for stars like the sun. Okay, so exhaust those inner resources. It will soon begin to die. This is really the last stage, where the evolutionary track becomes a dashed line and changes so rapidly that they're difficult to model. Okay, and this is the point also where it starts shedding huge amounts of matter from its surface. So the helium shell flashes. There's going to be tons and tons of matter coming off of the surface of the star. The idea there is that the escape velocity of the highly energized atoms, the very hot molecules and atoms bouncing around on the star's surface, that escape velocity is lower than their random kinetic motion. And so it just starts losing matter. It's just shedding hot gas that just isn't gravitationally pulled back to the star. And so it just starts becoming this huge swell of gas coming off of this unstable star that is about to die. Okay? So here's a picture. Okay, a picture of a star kind of right before death in its last stage. Okay, so this is interesting because it kind of shows that the star at its most complex stage, right before it dies. Okay, it's got a hydrogen envelope. This is kind of leftover matter that was never fused. It's got the shell fusion, but notice the shell fusion has got pushed back quite a bit. Where we saw the shell fusion before, it was kind of much closer to the interior. This is where fusion is going on. Here's the helium core. So the helium core has been, this is matter that isn't hot enough to fuse. This is kind of leftover helium that was pushed out of the way because now there's actually helium fusion going on inside, because as we go deeper, it becomes hotter. So this is where the actual helium fusion is being performed at that final stage. But after all that helium is producing carbon and oxygen, all that carbon and oxygen is going to sink down to the very center of the star, and there's never quite enough heat to fuse it. So it just becomes an inert, incredibly dense core that is just getting denser and denser and denser as gravity continues to pull it in. Okay? All right? And of course, the ultimate idea is gravity pulls something in as it becomes a black hole, right? A star like our sun never will, but we'll discuss that more in the next chapter. Okay? But some stars can. But you know how I mentioned the idea that the star becomes so big and so unstable, and those outer layers are so energized that their random kinetic energy is greater than the gravitational pull. So in other words, we say that their thermal velocity is greater than their escape velocity. Well, that produces something called a planetary nebula. Now that is the worst name in astronomy, or at least as far as I can think of, it's the worst name, because it has nothing to do with planets. And we already talked about exoplanets and things that actually have something to do with planets. But when astronomers first discovered these unusual clouds that exist around some stars, some of them were circular, and they thought maybe they were planets, and hence the name, and the name has stuck with us. But a planetary nebula has nothing to do with planets, and in fact, many of them have a shape of two lobes like this. And actually what they represent is that shedding matter from the surface of a dying star. Okay, and they're really common for stars that are around one solar mass. So stars like our sun, they're going to be the ones that are going to be going through those stages, becoming a red giant post the helium fusion, and they're going to really be forming that planetary nebula. Here, see some more pictures of them, right? And they're different depending on the perspective, right? If you look head on, they look like this. If you look from the side, we can clearly see the lobes. The lobes are formed by the magnetic field of the star. That's why. Okay, so if you want to kind of think of a key physical process that relates to that gas cloud around dying red giants, misnamed a planetary nebula, just think that it has to do with the magnetic field of the star, right? And stars have magnetic fields because they have a bunch of charged material that's spinning around at high velocity, so they generate that magnetic field. Okay, here's another beautiful picture of one. All right, so one of the last ideas here. What about stars that are bigger than our sun? What about those ones that left the main sequence, became super giants, hypergiants even is a term for the biggest red giants? What happens to them, right? Because they were bigger to begin with. They started off on the main sequence, way up at luminosities 80,000 times more luminous than the sun, right? They're the ones that burn hot, die young. Okay. Well, what about them? Well, they actually go through some other phases. because they were so much bigger, they had so much more mass to start with. When their helium core goes through fusion and starts producing oxygen and carbon, well, then that oxygen and carbon core collapses, but it's bigger. And so when it collapses, it actually collapses into a new core, and it starts fusion of its own. So let's look. We've got the hydrogen envelope. Then we've got hydrogen and helium fusion occurring in this region. Okay. Then we have a helium fusion, okay, which would have been, a helium core at some point, because at some point this star would have been a helium star, probably for less time, or less proportion of its overall life. But then look at this. Underneath the helium fusion, we actually have carbon-oxygen fusion. So there's enough energy to fuse carbon and oxygen into what? Into magnesium, neon, and oxygen. Okay. All right. So here's the thing. Oh, excuse me. So here's the thing. Some stars are so hot they can even fuse that magnesium and neon. And then you notice the oxygen kind of shows up twice. It just depends on the cycles of fusion. There's these processes that occur within fusion. So, but some stars are so bright that they actually then, that isn't the end of the line. That's not just kind of inert. They're actually able to fuse the magnesium and neon into silicon and sulfur. Now this is amazing, right? Because these are the 1% of stars that are actually big enough to fuse magnesium and neon into silicon and sulfur. But here's the thing. We have tons of silicon and sulfur here on Earth. I mean, the crust of our planet is formed primarily of silicon. So that means that all came from huge stars that then died and shed their matter, and then that matter accumulated around our sun later in the life cycle of the universe. It seems such an exotic origin, but that's where it came from. All right. And so, but that is truly the end of the line, because the hottest stars, then they can basically just continue to produce enough energy to fuse whatever, eventually will fuse silicon and sulfur into iron. But iron cannot be fused to anything else. Iron has a very unusual property where it has the least binding energy of any atom, which means that its nucleons cannot be fused into something that's energetically favorable. It is the energetic end of the line. And so iron cannot be fused. It will become an inert core called ash, because it's the byproduct, and that iron core will eventually collapse. And if that iron core is big enough, it can collapse into a neutron star or into a black hole, which will be the topic of the next chapter, because that's what we wanted to talk about in this chapter, was leading up to death with a focus on stars like our sun, right? But then including an idea that many of these ideas can apply to bigger stars as well. Okay? All right, so I hope that hopefully this all made sense and you saw that there was kind of one connected theme here. I hope it was an interesting lecture, and thank you so much for watching.